Okay, so next speaker is Varun Suryanarayanan. He'll talk about online load balancing with Recourse.
Thank you. So before I talk about online load balancing with Recourse, I know we've seen this plenty of times today, but I'll review it once more. What's online load balancing? In this problem, we're given a set of machines indexed 1 through m, and a sequence of n jobs arise online. We don't necessarily know n in advance. I'm just putting n there because that's the notation we'll use. Every job comes with a set of loads, Pij. We need to assign each job to a machine as it arrives. When it's assigned to machine I, it places load Pij, and the goal is to minimize the maximum load on any machine. Now, this problem has been studied very well, and about 30 years ago, a member of our audience there showed that you cannot do better than O of log n competitive. So in this special example, suppose n is a power of 2, Pij's are either 1 or infinity, jobs arrive in groups or batches. The first batch will have half n jobs, second batch 1/4 n, and so on. Each first batch will be serviceable on every machine, second batch on only the half most loaded machines, third batch on the 1/4 most loaded machines, etc. And the high level idea is after the ith batch has arrived, the most loaded machine will have at least I jobs on it. So here the first 4 jobs arrive, you assign them to 4 machines. Then the next 2 arrive, at least one machine will have 2 jobs on it. Then one more arrives and one machine has at least 3 jobs on it. Then the last job arrives and one machine will have 4 jobs. If we want to be more precise, it's log n base 2 plus 1. But the optimal solution would be to assign the jobs like that. Now, in the setting where this was done 30 years ago, right? So in recent years, there's been a focus on looking at the problem with recourse. The idea here is we're allowed to reassign jobs or shift jobs from one machine to another, but only a limited number of times. If I allowed order n squared many shifts, then the problem essentially reduces to the offline version where you resolve completely every time a new machine arrives. Now, because jobs can change machines, the goal changes from minimizing the maximum load on any machine at termination to minimizing the maximum load on any machine at any given point in time. So what's known about this? In a special setting known as restricted assignment, where every job is restricted to running on some machines, but whichever machine it chooses to run on, the load placed is the same, or Pij's and Pj infinity, it was shown by different members of the audience about 10 years ago that you can obtain a log nm competitive algorithm with linear recourse. This was generalized by later work by different members of the audience to a setting where each job has a weight and you want to minimize the weighted recourse. So our results, we prove a 2 plus epsilon competitive algorithm exists when you are allowed n log n recourse. And if you're allowed O of n recourse, then you can find O of log n divided by log n. The additional difference here is we do this for arbitrary Pij's. Any questions so far about the problem setup or nothing? Great. So for today, I'll focus on the constant competitive with n log n recourse. Is there a question? Weighted recourse means that each job has a weight, so shifting some jobs is more expensive than shifting others. Yeah, the definition changes slightly, but like the load of the job on machines and the costs, the recourse cost of shifting a job are two different things. Uh, um, I think that's it, right? Okay, so first I'm going to go over how our algorithm would work in an offline setting. The idea is we use min-cost generalized flows to find a fractional assignment first. Then using this flow solution, we construct a bipartite matching instance and we then solve, and then the flow solution would be a valid fractional solution to the bipartite matching instance, which means you can find an integral solution efficiently. So, flow. Unlike normal flows, in generalized flows, if I send one unit through an arc, I can get more than one unit out on the other side. Every arc has a gain on it. Now, in this specific network, we're going to have three types of nodes, one corresponding to each job, the one corresponding to each machine, and a global sink. The job machine edges will have gains Pij, cost 1, and infinite capacity. The machine sink edges will have gain 1, cost 0, and capacity 1 plus epsilon times T star, which is the optimal make span. The algorithm I will present here today assumes knowledge of the optimal make span. We have a way to work around that, but just to make things easier, I'll keep it this way. So the solution to this, we're going to send flows by cheapest augmenting paths until we send one unit of flow out of each job node. Now, unlike regular shortest augmenting path in flow problems, here an augmenting path can be either a source sink path or a path to a flow absorbing cycle, which is a cycle with gain less than 1. So is there anybody who's not clear on why a fractional solution to this flow problem corresponds to a fractional assignment with every machine having load at most 1 plus epsilon T star? Yes, you can. But for the online version, the jobs will arrive one by one. So, I mean, okay, even there you can use a linear program. It's just cheapest augmenting paths is easier to analyze in the online version. In the offline version, it's all the same. You can get an optimal solution efficiently. Okay, so how do we construct the matching instance? We're going to have one left-hand side node for each job. We're going to divide loads into buckets. So the first bucket will be like T star over 2 to T star. Second bucket will be T star over 4 to T star over 2, and so on. We let FKI denote the amount, the total fractional number of jobs with processing time Pij in bucket K that are assigned to machine I. Then we construct the ceiling of FKI, right-hand side submachine nodes corresponding to machine I and bucket PK. A job J will have edges to every submachine of machine I bucket BK if Pij is in BK, and it won't have edges to any such submachine otherwise. Questions on the instance or how it's constructed? Okay, so to see why the make span or the maximum load on any machine is at most a constant times T star, the fractional solution loses a 1 plus epsilon factor. Then for any we created most FKI plus 1 submachines corresponding to a given bucket if FKI was the total number of jobs assigned to that machine and bucket. So if I had used at most FKI, and there wasn't, okay, we lose a constant factor due to the buckets. Then because of the +1, we lose a geometric series that totals up to 2 T star, and FKI leads to an additional loss of T star. So we obtain a constant question. We don't need it for the offline version, but for the online version, we will need it. That's why I just kept it there. Oh. Yeah. Yes. No. You're assuming you know T star. We have a different algorithm that works around that, but for simplicity, I'm doing it this way. Okay, so how is our online algorithm going to work? It's going to maintain both a current fractional solution or flow and a current assignment or schedule, right? So when a new job arrives, you're going to send shortest augmenting paths from that new job or flow via cheapest augmenting paths from that new job to obtain a new fractional solution. Then you're going to update the matching instance and find a new bipartite matching to obtain a new integral assignment or schedule. Of interest in prior work was all like these two. So the generalized flow problem in and of itself is interesting, and for that problem, we can attain a constant competitive ratio with O of n recourse, while for the semi-dynamic matching problem, we get a constant competitive with n log n recourse. By semi-dynamic here, I mean left-hand side nodes only arrive, right-hand side nodes arrive and depart. So, question. Sorry? It works for arbitrary networks. For today, I'll just go over the scheduling version because that's the result we're focusing on. Residual graph will have flow absorbing cycles. Yeah. Okay, so the online problem, right? Sources will arrive one at a time, so we don't know all the sources up front. So cheapest augmenting path is slightly different in that instead of sending the cheapest augmenting path from any source, we send the cheapest augmenting path from the most newly arrived source until one unit has been sent from it. And another key difference we have is in traditional generalized flows, if I send one unit along an edge, then to pull that unit back, I would incur cost 1 again. I'd have to scale for Pij per unit, but here instead, the backward arcs are going to have cost 0. And the idea, the motivation for this is in our scheduling problem, if I'm shifting a job from machine I to machine J, that's one recourse operation. And I'll be paying the cost for making the new assignment. So no need to also pay the cost for pulling it off from the old machine. Okay. So 2 results I would need to convince you of are constant competitive ratio. Oh, was it a question, sorry.
Assignment. You have to take into account both recourse and reducing the load, right? So, or am I missing something?
Sorry, repeat the question.
You have 2 goals, right? You want to to minimize the load, the maximum load, and you want to minimize or bound the recourse, right?
Yeah.
So when you augment the flow, how do you take care of both?
Okay.
Both objectives?
So the machine sync edges and flow conservation constraints guarantee that no machine will ever have more than 1 plus epsilon T star load.
Okay.
And we are assuming we know T star. So that's not really an issue. The other unique feature of this is if I have n jobs assigned, the cost of the current solution is n, right? Which will come up in the analysis. So, okay, the fact that the flow gives you something close to the optimal make span is clear. What I need to convince you of is there's not too many recourse operations. So how am I going to prove this? First, I'm going to use the notion of a height, where the height of a node is the per unit cost of sending flow along the cheapest augmenting path from that node. Okay. And this is why the plus epsilon is important, because after sending 1 unit of, like, if I were to have capacity T star here and I had an optimal assignment, the heights of nodes could be infinite. But because I have that slack, I know they will not be. So heights are now I said, okay, heights or this cost of sending flow. First, I'm going to claim that heights are non-decreasing. And therefore, the heights at termination are an upper bound on the height of a node when it arrived, and an upper bound on the cost of, an upper bound on the total cost of flow sent out of that node. Then I'm going to upper bound the heights by using the fact that they constitute a feasible dual solution. And of course, the primal has objective value n, so the dual has objective value n. And then bound the sum of these heights by analyzing the dual a bit. How much time do I have? Seven, 8 minutes, okay. Fine. So heights are non-decreasing. The proof is going to proceed in essentially 3 steps, right? And idea is going to be, suppose I send flow along a F1 along a cheapest generalized augmenting path from some source. And F2 is the new cheapest generalized augmenting path from some node V, then V falls into one of these 3 cases, where it's either the source or a vertex on F1, but not the source, or a vertex not on F1. And for each, I'm going to prove that its height must have increased. So why would the source's height have increased? Suppose its height did decrease, and you've got a new flow F2 from the source that had per unit cost less than F1. Then originally, I could have sent F1 plus F2, and I can choose the cheapest generalized augmenting path or the cheapest component generalized augmenting path from F1 plus F2, and that would have cheaper per unit cost. One thing I've glossed over, just like how in regular flows you can decompose into sourcing paths and cycles, you can decompose generalized flows into a bunch of other things like unit gain cycles, bicycles, etc. And a little more work is needed, but you can show that this argument holds. The next case is when V is a vertex on F1, but not the source. Here, the idea is going to be that same flow F1 from source to V, but then if instead of sending F1 onwards from V, I sent a mix of F1 and F2, I would reduce the cost of the original generalized augmenting path, contradicting the assumption that the original generalized augmenting path was cheapest. Similarly, if a node is not on a node V is not on F1, then its new cheapest generalized augmenting path must use a backward edge that was created by flow F1, which means it must reach a node that was reached by F1. But the height of that node did not decrease, and the cost of the path to that node has not decreased. So this vertex V's height could also not decrease. Are there any questions now? No? Okay, good. So upper bounding the heights using the dual. High level idea here, I've just put the equations there for anybody who wants to check. First things first, the correct dual should not have the 1 plus epsilon in the denominator there. The reason I can afford to add that without changing objective value is there is a solution to the flow problem which only sent T star units along each machine sink edge. So if I reduce the capacity of the machine sink edges, which are the only ones with finite capacity, the objective value of this problem would still be the same as the objective value of the true dual, which is n. Now, to show the rest, I want to show that the sum of mu e ze is at most the sum of the heights. The first term there is essentially the sum of the heights. Right, and to show that this sum of mu e ze is at most sum of the heights, I use the fact that the backward arcs cost 0, and therefore, if a job was fractionally assigned to a machine, then the machine's height is at most the job's height scaled by Pij. Then I take an average, then sum over all of those, and I can show that the sum of these machine heights, which are an upper bound on the sum of the z's, is in turn upper bounded by sum of the source heights. And therefore, sum of the source heights is at most O of n. Okay. So now, how do I construct the correct matching instance or the online matching instance? The difference here is there's two key differences from before. I need to construct two FKI many submachines instead of FKI, and I need to add this uniform random variable row. The reasoning is adding the random row ensures that in expectation, we delete at most 2 FKI new minus 2 FKI old many submachines of machine I bucket BK. And every time a submachine bucket node is deleted, that leaves at most one job without a machine that it's assigned to. And by adding in this factor of 2, I ensure that the graph expands sufficiently fast that the shortest augmenting path to assign this now unassigned job is at most O of log n in length. And that gives us the recourse bound. The bound on the make span is very much the same as before. And that's pretty much it. So, I mean, any questions now? Oh, yeah, sorry.
You're basically doing something. You're in your proof, you're doing some kind of dual fitting, right? Is that the right interpretation?
Yeah.
So why doing the dual fitting with respect to the generalized flow is better than working with a standard LP?
With the standard LP, are you talking about the 1 plus epsilon factor there or something else?
About the whole thing. What do you gain by working with the? You said that it's important for the online version working with a generalized flow.
Yeah, so the idea is, how do I translate? So I'm sending 1 unit of flow out of each job, but I want to bound the outflow from the machines in terms of load or processing time, right? So the only way to say that like let's say job 1 has load 5 on machine 1 and load 10 on machine 2. If I'm sending 1 unit of if I'm assigning job 1 or sending 1 unit of flow out of the node associated with job 1, how do I ensure that there's 5 units reaching job 1 but 10 units reaching job 2 if I assign it that way? So I need to use generalized flows. But did that, I don't think I've answered your question completely.
I thought you said earlier that you can write a standard flow or min cost flow formulation for the problem.
I meant min cost generalized flow for this problem. If in the restricted assignment setting, this does become a regular min cost flow LP, which is because these processing times vary, you need to have generalized flows.
Okay.
Question.
So if I want a competitive ratio of 1 on the online generalized flow, what's known for recourse?
Sorry?
If I want a competitive ratio of 1 for the online generalized flow problem, what's known for the recourse?
So I don't think anything's known for the online flow itself. I mean, bipartite matching is a special case of this, right? Or bipartite B matching, let's say. And in that setting, log squared n recourse, like shortest augmenting paths is known to need at most log squared n recourse, or n log squared n recourse, log squared n amortized. And it's conjectured to be log n amortized or n log n total recourse operations. But for the more generalized flow problem, I don't think anything's known.
Thank you.
Do you get better results for the restricted assignment model, or it's the same?
It's the same. Like we don't have improvements for that special case. Yeah.
So this is, excuse me, insert only?
Sorry,
This is like an insert only model, right?
I didn't catch it.
Insert only,
Insert only,
right?
as in, what do you mean by insert only?
Like jobs only arrive?
Yes, jobs only, right?
Can you say anything about the fully dynamic case?
No, we tried, but we couldn't.
Okay.
Yeah,
Thanks.
like, I mean, a complexity there is so this idea used the fact that you could consider heights at termination, right? But if jobs can depart, then heights at termination is not appropriate anymore. And that's why this fails. But I don't know of a way to extend to that setting.
You're not just guessing and doubling T star, right?
Sorry?
So you said you have a way around like the fact that you are assuming you know T star, and it's not
Yeah.
just guess and double, right? Because then you lose another factor too.
It's a little more than that.
Okay.
But yeah.
If I didn't care about being like, another constant worse.
Guessing and doubling works.
Yeah.
But
okay.
there are other ways to refine the
Got it.
constant. But
Thank
yeah.
you.
Right, let's thank the speaker.
Okay. Oh, sorry.